all what we have taken up till now, we use a half cell and connect it to a standard hydrogen electrode reference cell in order to measure its standard electrode potential. But what happens if we connect two different half cells together? We get what we call the electrochemical cells. It's not anymore half cell, but we get two half cells, two different half cells, and we connect them together and see what will happen. We call these electrochemical cells. Now, for example, if we get two half cells like copper metal placed in a solution of its own ions, copper ions, 1 mole per decimeter cube, and we get a zinc metal and place it in a solution of its own ions, zinc ions 1 mole per decimeter cube, and we connect them by wires. And of course, we have to connect them by a salt bridge so that their solutions be connected and a closed circuit will be formed. Now, when we measured the standard electrode potential of zinc, it was minus the standard electrode potential of zinc ions. Zinc, you see that usually the half cells are written so that the ions are written first and then the metal. Zinc ions Aks, zinc metal, we see that the E node value is negative 0.76 and the copper is positive, the copper ions positive, copper is positive 0.34. So what do we deduce from these two values? That the zinc ion zinc half cell has a standard electrode potential of minus 0.76 volts, and that of copper ions copper is plus 0.34 volts. What do we deduce from these two values? Do you know?
Zinc is more reduced.
It means that zinc would prefer to form zinc ions, isn't it?
Yes.
That zinc would prefer to form zinc ions. If we want to draw it, we write it in a reduction form. We say that zinc ions plus 2 electrons gives zinc metal. We find that the E node value is minus 0.76 volts. This means that the zinc would prefer to be oxidized to form zinc ions plus 2 electrons. It means that zinc releases electrons to form the zinc ions. But on the contrary, we will find that the copper ions plus 2 electrons gives copper metal. We find that the E node value is plus 0.34 volts, which means that this reaction
it likes to be reduced.
Yes, that the copper ions would like to be reduced, isn't it? So this means that electrons are coming out from the zinc half cell because the zinc would prefer to dissolve to form zinc ions, and electrons come out from this electrode. Okay, when we write here that zinc ions plus 2 electrons give zinc, the value is negative. This means that the zinc metal would prefer to form zinc ions and electrons, and the electrons go through the circuit to the copper half cell, where the copper ions in the solution would gain 2 electrons to form copper metal because we got a positive value for the standard electrode potential. Okay. Understand? Okay. So this means that we call this the electrode where electrons comes out of it. We call it the negative electrode. We call this the negative electrode because electrons are coming out of it. We call it the anode. The anode here is the negative electrode in electrochemical cells, and the copper is the positive electrode because it will accept the electrons. It is the positive electrode, and we call it the cathode. It is opposite to electrolysis. Here, the electrode where electrons comes out of it is called the negative electrode, and it is the anode, but the electrode that accepts electrons is the positive electrode, or we call it the cathode. So from the values of standard electrode potential, we can determine the flow of electrons. We can determine the flow of electrons, okay? And determine which one is the negative electrode and which one is the positive electrode. But if we want to measure the electromotive force, or the standard cell potential, we call it the standard cell potential, then in that case, we say that the standard cell potential, which is E naught cell, if we place here a voltmeter, a high resistance voltmeter, so that to measure the standard electrode, the standard cell potential of this cell, we say that E naught cell equals E right minus E left. What is E right and what is E left? The E right is the electrode, which we call it the positive electrode or the cathode. This is the E right. The positive electrode that accepts electrons, that has the more positive value, will be this E right. This is the E naught cell, is the standard cell potential, is equal to the standard electrode potential of the right-hand side electrode, which is the cathode or the positive electrode, and the E left is the anode or the negative electrode. So here we will see that it is equal to E right, which is plus 0.34 minus, and then E left is minus 0.76. If we add these together, we get 1.1, we get plus 1.1 volts, isn't it? So we call this the standard cell electrode, the standard cell electrode. Understand?
Yes, sir.
Okay, so always in order to measure the standard cell electrode between the standard cell electrode between two different half cells, then we say E naught cell equal E right minus E left. E right is the standard electrode potential of the right-hand side electrode, which is the electrode that accepts electrons, minus that releases electrons, we get the E naught cell. So here we have two half cells, two redox systems. Zinc ions plus 2 electrons gives zinc metal. E naught is minus 0.76 volts. And copper ions plus 2 electrons gives copper. E naught equal plus 0.34 volts. So when we connect them together, we get the total cell will be that we are going to add these two equations together. Of course, we are going to leave the more positive when we want to write the total E naught cell. Okay, I'm going to return back to this part. Here we have these two half cells. So sometimes they ask us to write the total cell reaction. This is called a half cell reaction, and this is also called a half cell reaction. And when they tell us to write the total cell reaction, we leave the half cell that has the positive or the more positive value, because sometimes both of them are positive, but we keep the one having the greater positive value as it is. So we say copper 2 plus 2 electrons give copper. E naught value is plus 0.34 volts. We leave the more positive as it is, and we flip the other one. We make it the opposite. So zinc gives zinc ions plus 2 electrons. And as we flip the first half cell, we also change its sign to be plus 0.67 volts. And then we add these two equations together. The electrons on the left-hand side cancels with the electrons on the right-hand side. And the total cell reaction will be copper ions plus zinc metal gives copper metal plus zinc ions. And if we add these two values together, we get the E naught cell to be as I as I calculated it before, the E naught cell to be equal to plus 1.1 volts. It's the same, either we write E naught cell equals E right minus E left, the one with the more positive value minus the one with the less positive value, or else when they ask us to write the total cell equation, then we have to write both equations. The one with the more positive value, we leave it as it is, and the other we flip it. We flip it so that zinc gives zinc ions plus 2 electrons, and as we flip the half cell equation, we also change the sign of the E naught value to be a positive instead of a negative one. Okay.
Okay.
Now, what are cell diagrams? When we want to express our cells, we usually write them in something called shorthand notations. We are not going to write everything, but we write shorthand notations so that to express our cell diagrams using words or using symbols. So this is called the cell diagram. For example, if I want to express the zinc half cell electrode, so I'm going to write zinc ions aqueous, and then we put a slash and then zinc solid. This cell diagram notation expresses that we are having a half cell containing a zinc metal placed in a solution of its own ions, zinc ions. And we write E naught equal minus 0.76 volts, which means that when we measured its standard electrode potential against a hydrogen electrode, the value was found to be minus 0.76 volts. The minus value means that the zinc would prefer to ionize to zinc ions. It will prefer to be oxidized to zinc ions because it has a negative value. So this is called a shorthand notation, or we call it a cell diagram. Okay, to represent this half cell. Now, if, of course, this solid line represents the interface boundary between the metal and the solution. This solid vertical line represents that there is a boundary, a phase boundary between a metal and its solution. Okay, here are other examples. If we have magnesium ion, then a solid line, magnesium solid. This means that this half cell is of a magnesium metal placed in a solution of its own ions that are magnesium ions, and the E naught value is minus 2.37 volts, which also means that magnesium is a reducing agent. It would like to be oxidized to form magnesium ions because the value is negative. Here we write this cell diagram notation that the copper ions aqueous, copper solid. E naught value is plus 0.34 volts. It means that copper metal is placed in a solution of its own ions that are copper ions against a standard hydrogen electrode. This vertical solid line represents the phase boundary between the solid and the solution. And the E naught value is positive 0.34 volts, means that the copper ions prefer to be reduced or gain electrons to form the copper metal, which means that it is an oxidizing agent. Aluminium ion, solid aluminium, solid vertical line means that there is a boundary phase between aluminium metal and its aluminium ions in the solution. E naught value is minus 1.66 volts, also means that aluminium is a reducing agent. It would prefer to be oxidized. Silver ion, silver, E naught value plus 0.8 volts means that silver ions are oxidizing agents because they would like to be reduced to form silver metal, and this is shown by the positive value of the standard electrode potential. This is when we write half cells. These we call these cell diagrams of half cells. We only represent only one half cell. Now, what if we have a half cell, but instead of a metal placed in a solution of its own ions, we have two ions dissolved or aqueous solutions. And we were measuring the standard electrode potential between these two aqueous ionic solutions. So how are we going to write this cell diagram, half cell? If you remember, when we used two aqueous solutions, in order to connect them with the standard hydrogen electrode, we used platinum wire. It will be our solid connection with the standard hydrogen electrode. That's why we're writing this cell diagram, half cell diagram. We will write at the beginning platinum, because we used platinum metal to be placed in the two solutions, the mixture of the two solutions of iron plus 3 and iron plus 2. You remember how did we construct this half cell? Or shall I draw it once more?
One more time.
Okay, so here we have a mixture of two solutions. That's why we write iron plus 3 aqueous and then comma iron plus 2 aqueous, because both are present in the solution as a mixture. And we placed platinum wire to be our connection with the standard hydrogen electrode. So at the beginning, we write platinum solid, and then this boundary phase, vertical line, to represent there is a boundary phase between the platinum wire and the solutions. We write iron plus 3 aqueous, comma iron plus 2 aqueous, and the E node value is the positive value, plus 0.77 volts. Of course, all these potential values are present in the data booklet. They will always ask you to use your data booklet. Now, here between the iron plus 3 and the iron plus 2, there are no phase boundaries. That's why we put a comma, because both of them are solutions. There is no phase boundary. Now, for the standard hydrogen electrode, we write hydrogen ions aqueous, then this phase boundary, half hydrogen gas, and then we write the platinum. This is opposite to what we did here. In the half cell of using iron plus 3 and iron plus 2, we wrote the platinum first. But for the standard hydrogen electrode, we used to write the hydrogen ions, hydrogen gas first, and then we put the platinum. So hydrogen ion aqueous, phase boundary, because there is a phase boundary that separates between the hydrogen ions and the hydrogen gas. And then there is another phase boundary to put the platinum wire. Okay, so always in all the above equations, we will see that the reduced forms are shown on the outside of the cell diagram, and the positive electrode is shown on the right-hand side of the cell diagram. Now, what happens if we want to write the cell diagram for an electromotive cell or electrochemical cell? It means two different metals are placed in their solutions. We have two different half cell electrodes. So how are we going to write them? We know that zinc is the electrode that releases electrons, and we call this the E left. We call this the left half cell. So usually the electrode that is going to release electrons is going to be written first. So we write zinc metal, then phase boundary, zinc ions. You see in the half cells, we write the ions first and then the metal. But in the cell diagram, we write first the electrode that releases the electrons. We write it first, but we write the zinc metal and then the phase boundary and write the zinc ions, aqueous, and then we put two vertical lines, dotted lines that represents the salt bridge. This represents the salt bridge that is between the zinc ions, copper electrodes. So we write the metals at the terminals followed by phase boundaries, and write the ions, aqueous, and between the ions we put two vertical dotted lines. It means that here we have a salt bridge to connect these two half cells. Okay, understand, or shall I repeat anything?
Understood, miss.
Okay, so here we write below the half cell of the zinc ions, we write its E0 value to be minus 0.76 volts, and that of copper ions, E0 equal plus 0.34 volts. And now to find the E0 of the cell, the total electromotive force, or we call it the standard cell potential, we get the E left minus the E right. The E left, sorry, the E right minus the E left. So the E right is plus 0.34 minus the E left, which is minus 0.76. We get it 1.1 volts. Now, what is meant by the difference between two standard electrode potentials? Of course, when we have a certain electrode potential and another, the difference shows the difference in reactivity of these two metals. For example, if we have two half cells, we get the difference, we get the difference in reactivity between these two metals. Now here, when we write the standard electrode potentials, it means that we get a metal dipped in a solution of its own ions, and we measure it against the standard electrode potential. Here we have to follow this rule that always the standard hydrogen electrode should be written on the left-hand side, and the other half cell should be written on the right-hand side. The standard hydrogen electrode is always written on the left-hand side and the other on the right-hand side, whether the E0 cell is negative or positive. We do not mind the positive and negative here because we are writing cell notations or cell diagram notations for measuring the standard electrode potentials of any half cell. We usually put the standard electrode first, and the standard hydrogen electrode first, and then the other half cell. So here, for example, platinum, then we put the solid line, half hydrogen gas, we put the solid line, H positive aqueous, and then the salt bridge, which is represented by two vertical dotted lines, and then zinc ions, zinc metal. The E0 cell is minus 0.76 volts. And we will do the same for the copper half cell that is measured against the standard hydrogen electrode. We write platinum, half hydrogen ions, and then copper ions, aqueous, and copper metal. As you see, we put the solids at the terminals together with the solids, which is the platinum solid, and then the gas, and then the ions in the middle, like as we did here. Both metals at the terminals and the aqueous solutions in the middle, separated by the salt bridge. It's opposite to what when we wrote the half cell electrode of the standard hydrogen electrode. When we wrote it alone, we wrote hydrogen ions, half hydrogen, and then platinum. But if we write it in presence of measuring together, when it is together with another half cell, we write it in an opposite way. Platinum, half hydrogen, hydrogen ions. Okay.